Log on, tune in, find out. Another good idea from Cambridge.
Yes, so my name is Joakim Nyberg and I'm from Uppsala University. So this is work done together with Sebastian Reckert, who presented.
Did you turn on mic?
I think so, yeah. It's on. And Andrew Hooker. And the reason why we started to look at this, and you've seen this before, is because that we compared these different softwares, and this first order approximation didn't really work well when we used this, what I will call the full Fisher information matrix. We take the derivative of the variance with respect to the fixed effects, or if we don't include this term. So that's really the reason why we started to investigate this. And in this talk I will try to make some other approximations that might solve this problem, at least locally.
And maybe move the microphone a little closer to you.
Higher?
Yes, need to speak louder too. Let your voice boom.
Is it better?
Yeah.
Yes.
Good. So, I will actually do quite a lot of background here, initial problems, and try to talk about the nonlinear marginal likelihood and different ways to go from there to the Fisher information matrix for a linear Gaussian. So we know that analytic solutions exist for linear Gaussian mixed effects models, but obviously not for a nonlinear. And if we assume normality, we can calculate the population likelihood, or the likelihood, by first order linearizations. We can use Laplace integral approximations, might use Monte Carlo techniques, or EM algorithms, Gaussian quadrature, etc. So the first slides will be about notation, how I say about this. And for individual I, we have a structured model, and we have some residual error model. So here I don't write homoscedastic or heteroscedastic, but just the general residual error model. If we look a bit more about structural model, we can have, for example, a PK example, so concentration time profile, this simple function here, 2 parameters, clearance and volume, and they are different for different individuals. In this example, I just simulate 10 individuals with the same design, but clearance I and VI was different. And we can go to pharmacodynamic example, effect versus time, for example. We have 3 parameters, baseline, Emax, EC50, and again, I use the same design parameters when I simulate this. If we look more deeply into the individual parameters than the clearance I and volume I often write typical, so the population, typical value of clearance, and then some transformation of an individual sample from a normal distribution, from a variance for this parameter, clearance in this sense. And you can do the same for the other parameters. Of course, this could be an additive term, proportional, or any term you think of. So call this the typical individual parameter, and this is actually the blue line here, where this eta value is equal to 0. And we have some inter-individual or between subject variability coming from these 2 variances. And finally, we have the first the typical profile, inter-individual variability, and then we have some residual unexplained variability. So RUV is what I will call it. And in this case, it's just 10 samples equally spaced in the time, and I just simulated residuals proportional to the response. So if you have a higher response, you will have a higher residual error. Again, we describe this with a sigma term here, and that's representing the variance. So the population parameters we are interested in is the fixed effects, so the theta values here, the random effects, and that will be the inter-individual variability and also the residual unexplained variability. So if we then look at the population likelihood, that's just the sum of the marginal log likelihoods for all individuals, given the population parameters. And the issue here is the marginal likelihood that we really can't calculate. So we have the marginal likelihood, that's the individual likelihood, so that's just a PDF of the individual with some variance coming from the residuals, and we have the probability of an individual value from this normal distribution around 0. So it's the PDF of that. So a way to calculate this population likelihood might be to use the Laplace approximation then. So if we do this in one dimension, we call this product density. So we have this function that we want to calculate the area under the curve here. We can just Taylor expand this, or the log of this. And if we do this with a second order Taylor expansion, we'll get first order derivative and a second order derivative. But if we do this around the peak, we will get rid of this first order term, because at the peak the derivative will be 0. So then we just have the second order term there. And then we can approximate this by an unnormalized Gaussian, and we'll get this formula. So this joint density at the peak and some second order derivative. So the Hessian in matrix notation of this peak as well. And finally, we can approximate this normalizing constant with this the normalizing constant of Q. So we will get this formula. And this is basically how it will be. Another way of thinking about this is to use a linearization of the model. So again, we have the model here, the structural and the residual error model. And we can just, and in this case I will actually linearize around the residual error as well to make it a bit more general. So you can linearize around the residual error model first order linearization, for example. And then we do the same, but we linearize this around the individual parameter vector as well. So we get quite a lot of formulas, and to make the notation a bit more easy, I will skip this interaction term, and this is if you have a heteroscedastic model, for example. I will also skip this term, and this only comes in play if you have an exponential error model. So as I said, I skipped those two terms, and then we can sum them up in the expectation values. So we have this response value at this eta hat, so where we linearize around, and some derivative of that function. And with the standard formula, we can just calculate the variance, and we'll come to an expression looking like this. As I said, if you have this extra term here, you will have some extra term in this part as well, and Sergey included that in his slide, I think. And the last step then to calculate the marginal likelihood is just to assume a normal distribution with this expectation value and this variance. So that's another way to go from calculate the marginal likelihood. A further extension of this linearization is to do that around this eta hat equal to 0 instead. So if we do that, we will actually get rid of this small term here that we had before. So if we look at this term here, because eta is equal to 0. And also, we will calculate the variance, all this function here, evaluated at eta equal to 0. So that it's even more approximated, I will say, marginal likelihood. And we can also use the Laplace approximation and try to do that around this eta value equal to 0. But the problem is then that this first order term will not be 0 because we are not linearizing around the peak anymore. So we have to take that into account. And also, if we really want the first order linearization, we have to do something with the Hessian here. And a common way to do is to approximate that with a gradient product of the first order derivative evaluated at this eta equal to 0. So actually, if you do this, you will end up with the exact same marginal likelihood. So it's just two ways to look at the same thing, basically. So, and then Franz and many others as well extended this formula. Ritu, Hooker, Leonov, Ugenbenro, for example, calculated the Fisher information matrix, assuming that we have a linear Gaussian model. If you do that, you will get quite nasty terms, depending on the expectation and the variance. And you will have this block matrix, as many already showed, where we have the fixed effects and the random effects and the correlation between the fixed and random effects. So as we already mentioned before, we can calculate this in two different ways. So one way where we assume that there are no correlation between the fixed and random effects, and one that where we don't assume this. So basically, it's assuming that the derivative of the variance of the data is depending on the fixed effects or not. Also, if we do this, we will get some extra term up in the fixed effect part if we don't assume that the variance is independent of the fixed effects. And this extra term is here. So, what we saw then when we compared these different softwares with the full approximation or with the reduced approximation with the FO, we saw that the performance of FIM with the full was actually worse than the FIM with the reduced approximation. And that's not really, at least not what I expected, because in nonlinear mixed effect models we actually do have correlation between the fixed effects and the random effects quite often. So that was a bit surprising. So then we tried to figure out why that could be. And we found out that linearizing around the typical in is probably not enough. And Tobias talked about this as well. We also saw that the second order linearization around the typical value was not enough. So we tried that last pod. And then we thought, what about conditional approximations, where we maybe do the first order linearization but do it on the mode of this marginal likelihood. Also, Sergey also talked about a paper where they show this. The FO approximation with the reduced seems to work very well and predict the empirical precision very well most of the times. So the FO approximation is, as everything else, always already been published. So basically, take the expectation of the population FIM over the individuals. So basically what you're doing, you sample individuals from the inter-individual variability. You calculate the Fisher information matrix, where you linearize around this sample, and you sum them up or average them. So the Fisher information matrix is calculated, or the expected value and variance is calculated at this eta hat, the sample you take from this inter-individual variability. And this is a quite nice approach, I think, because we only need to simulate data, or only need to simulate individuals, not any data. And obviously we use, or possibly we use a more accurate approximation of the marginal likelihood in this case, because we take this extra term into account. However, it doesn't linearize around the mode, and that's what, if you do estimation with FOC, that's what you will do. And the derivative of this marginal likelihood with respect to the population parameters, and that's what you will use when you calculate the Fisher information matrix. So this block A, B, and C doesn't really update this eta sample automatically, because you don't have any correlation between the population parameters and the fixed effect and the individual sample here. So obvious solution would then be to try to use the same method or linearization method and calculate that around the mode instead. So that's what we tried. And as I said before, the mode of the marginal likelihood here is just maximizing this function, because then if you maximize that, you will be at the peak. And this could be calculated by, I call it empirical base estimates. And so maximizing this function with respect to the individual sample here. And I think this is similar to what you do in your paper from early 1990. So obviously one issue here is that we have a y here. So we need data to do this. Of course we can use simulations, simulate data and calculate this, but it would be nice to be able to do it without simulating data, because then potentially it might be much faster, of course. So then we thought of, because when we're calculating the Fisher information matrix, we are integrating over all data for all individuals. So if we then approximate the data for one individual by the median of that individual, or often the mean as well. So we say that the expected value of one individual is the median response for that individual. And then instead of using data, we use this median instead. So the residuals now in the individual likelihood is not strictly are now model dependent instead of data dependent. And if we do this, then it's obviously straightforward to get new eta hats when we take the derivative with respect to the population parameters, because we can just differentiate this a bit numerically, and then we'll get a new eta hat. So we'll get some additional information to the Fisher information matrix by doing that, because now we have a correlation between the eta hat and the population parameters. So if I summarize this FOC around the mode, for each individual contribution to the Fisher information matrix, so FIM-I, we sample individual from the inter-individual distribution. We calculate the expected mode around the median of this response. And we're calculating FIM-I using the FOC approximation, so where we take this extra term into account, so the derivative of the response with respect to the sample. And we can also update this EBs now when we differentiating to calculate the Fisher information matrix. And finally, we do exactly what France and Sylvie Retou did. We just Monte Carlo integrate over this Fisher information matrices. So again, it's the same example as before. We POD 2009 evaluated this warfarin problem. It's just first order compartment, one compartment with first order absorption, and we had a proportional error model and a fixed design, 32 subjects, 8 measurements, and we saw that actually the largest difference was in the fixed effect Ka parameter. And so we fixed all other parameters except that, just to make the problem very simple. So we say that all the other parameters are non-constants, basically, even the variance parameters. And then we calculated the truth by simulation estimation, this time with the FOC method in software called NONMEM. And we got the empirical relative standard errors for this parameter. And we evaluate this with a full Fisher information matrix, so what you think should be better, and we got quite far off from the relative standard errors. And we evaluate this with a reduced, and we were quite close. And then we used the second order approximation. It was a bit closer, but not really. And with the reduced Fisher information matrix as well, and it's quite similar here. And then we used the old FOC method, where you're not linearizing around the mode, and it's very optimistic in this case for the full Fisher information matrix, and also for the reduced. But then we used the FOC around the mode, and then we got very, very close to the empirical standard errors. And here I actually have an interval because it gave some different results depending on which samples I sampled from this inter-individual distribution. Another example, France will talk more about this. This was the PK part of this HCV model that Sergey showed as well. And it's a 2-compartment model, repeated dosing by a fast infusion. We used a linear ODE solver, so just matrix exponentials to calculate this ODE system. There was 6 parameters, 1 residual error, and I think it was additive in this example. If we then compare the different approximations, and we had the simulations here, so basically the truth, and we can look at the FO reduced and FO full, and it's a bit different. And here we actually look at the D criterion, so the determinant of Fisher information matrix to the power of the number of parameters, 1 divided by the number of parameters. And we see the old FOC method performs quite bad again with the reduced and the full Fisher information matrix. And finally, we can see that the FOC around the mode now gets very close to each other. So the FOC around the mode is quite close to the FO approximation if we do this, or at least closer. And finally, we look at the more nonlinear, in a sense, model, and this is the Emacs model. So it's just an Emacs parameter, and this is time, and you have a gamma factor here, so it's raised to a power of this gamma factor. In this case, we assume that this gamma parameter was a fixed constant again. So we're only interested in estimating the typical population EC50 and the inter-individual variability of this EC50 value and the residual variability. And I should say that we had a additive noise as well. We used 2 individuals and quite sparse design, so we only had 2 samples per individual, and we used local d-optimal designs. So now we can actually optimize with this and see if there are any differences in the optimal designs as well. Here you see just some simulations from the model. So it's effect versus time again, 100 simulations. And you can see that's quite a lot of variability, and the EC50 value is basically where you have 50% of the effect, the time where you have 50% of the effect. So it varies quite a lot. And because it's only 2 samples, we can look at the determinant surface with a different approximation. So it's sample 1 and sample 2 for the different 4 approximations here. And this is the first order approximation, the surface of determinant of Fisher information matrix. This is the second order. This is the old FOC method, and this is the FOC around the mode. So it's not actually in this case extremely unsimilar, or they are quite similar in this case, even though the optimal design here is maybe 35, 25, and in the FOC case for both of them it's 30, 30. The SO actually seems to perform, I mean, we don't really know the truth here, but the FO is quite different from the other methods as well.
I cannot see on this bottom right-hand corner there are 2 maxima.
No, it's only one.
The
So-
replication? The
Sorry?
maxima is 30 and 30, so
Yeah.
only 1 point?
Yes. So 30 for sample 1, 30 for sample 2. And for FOC it's 30, 30 as well. Here it's 35, 28 maybe or something. And this is very different. It's 22, 40, 45. So it differs, I mean, in percentage of the design space is quite different. So obviously a problem when you're using FOC around the mode is that you have to use the empirical base estimates. And when you're using empirical base estimates that is depending or estimated from the population parameters and data, you might get shrinkage. And you can think that you even get more shrinkage when you take this, so you're really not using the data, you're just using the median and try to calculate the empirical base estimates. So here we can simulate a lot of individual values and look at the shrinkage of the estimated expected EBs in this case. I did it with residual error and took the mean just to see that the expected EB is the same as doing it by taking the mean of many expected EBs. So simulated a lot of individual values and calculated the mode basically, or the expected mode. And if you really would get back exactly what you simulate with, you should be on a straight line here. But obviously it's quite a lot of shrinkage for this model. And this was done at the 30-30 point here. We can also look at the residuals we will have when we're estimating. And it looks, I mean, then we will have eta values all over the place here. Still quite a lot of shrinkage, but at least we will have more values in the outer border here. So implicit assumption here is that the information is symmetric around this EBE values. And obviously it will not be that. So if we then look at the result of this 30-30 point, even though we have this massive shrinkage, I would say, we can see that the FOC method performs very well if we compare that to the truth. Here we look at the relative standard errors, and we have this different approximation methods again. And this is the fixed effect EC50 parameter. If we look at the random effect, you have the truth up here, and the FOC mode and FO seems to perform very similar, and then we have the FO and SO is very similar. And finally, we can look at the residual error, and that's very easy to estimate in this case. So it's very similar for all of the 4 methods. So just to conclude and get some pros and cons with this FOC method around the mode. It addresses the full and reduced issues, at least in some part. So we can see that when we do this around the mode, the differences between the full Fisher information matrix and the reduced is vanishing. So it's somehow encouraging. It possibly gives more realistic predictions of the precision, sometimes at least we saw. The optimal design might be more accurate. Of course, it might not as well. We have to really investigate this for more models. It's obviously slower than the FO method because that's analytic. It's also a bit slower than the FOC because we not only take samples, we have to calculate this empirical base estimates. However, that's quite fast though. Obviously, we could suffer from shrinkage, even though unexpectedly, I would say we didn't see that here. And if we have, very sparse and uninformative designs. And yeah, as I said before, there's no closed form solution as in the FO-based Fisher information matrix. So if I were to use some method, which one should I use, or would I use? So the basic, I will use the FO-based reduced method in most cases, whenever it's possible. Sometimes you actually have to use the full Fisher information matrix. So for example, if you have autocorrelated parameters, so you have a fixed effect in the variance only, so autocorrelation fixed effect parameter, intrinsic variability, then you can't really use the reduce because then the Fisher information matrix will be 0 or infinity. But after optimizing, I will try to evaluate with the FOC around the mode method to hopefully get better predictions, or at least check the predictions of the relative standard errors. If not, if I can't use the FO method reduced, then I will try both full and the FOC around the mode. And if we get similar results there, I will use the FO, of course. And if we don't, maybe you have to use the FOC around the mode method to optimize as well. So that's all. Thank you very much for your attention.
Any questions?
Where'd you get the photo? Or where'd you take the photo?
No, I actually got an email with 10 of these photos, different photos, very, very bad designs from a friend of mine. So.
Questions to Joakim, please.
Yep.
In your previous slide, well, how do you know when you say use the FO-based reduced FO whenever possible?
Yep.
How do you know?
No, yeah. So one thing, obviously when it's not possible is if you have a fixed effect only in the variance part, then you have to use the full. So that's one answer. To know which is the best on beforehand, that's impossible, I would say, at least for me.
But when you're comparing against simulation results,
Yeah.
Can you tell a priori whether it's going to be reasonable to base your design on one method or another? If I don't know, then I'm going to have to compare various methods. In that case, I'm probably going to want to go with the one that's more reliable.
Yeah. Yeah.
The FOCE at the mode.
Yeah. But yeah, you're right. But it could be that you have to wait for a couple of months for your optimum design if you do that. So. And then, if you don't have that time, then you might do something faster, but more approximate.
So, on that point, because then if you had some arbitrary design you had originally and evaluated it only with an FO method and did a quick simulation estimation and then see how close standard errors were, assuming the question therefore is how much will the design alter the performance of FO reduced?
Yeah.
As in when you change the sign, it becomes more
Exactly.
sparse.
And I mean, I think it's impossible to know. And it's very different for different problems, of course, different models.
So, but my comment is, after 3 years of struggling through this, I'm impressed you come up with the conclusion which we wanted from the beginning.
Yeah.
If I reduces the answer.
Not always.
No, not always, no.
In terms of computation time,
Yeah.
can you give an idea what it took for?
Yeah, I mean, if you compare the previous FOC method versus FO, that's only almost linear to the number of samples you take to calculate this FOC. So if you take 100 individuals to calculate it, it's 100 times slower, basically.
But for
For this method,
for example, we did
for the example we did. So
for this one compartment model.
yeah, that was really fast, also with the FOC method.
So it
And all,
seconds.
yeah, seconds. And this Emacs model was also fast. But the PK, when we had a ODE, even though we solved it with matrix exponentials, was a bit slower. Can't remember the exact time now, but it's more minutes or
Because of the numerical solution.
numerical solution. Yeah. Yes.
Yes, thank you. So I have two comments. The old FOC that we did with Sylvia, I think, was wrong, because it's even worse than the FO, and
No, but-
we forgot about something, and so we can
But
more or less
actually,
forget about it.
I think it works. I mean, for some parameters, it works quite well, actually.
Yes, but it was never better than the very simple one.
No.
So let's go to the same.
I mean, maybe in this case, actually, but
Well, and then the second question is, well, it was too difficult for me to try to really follow both your question and Tobias, but at the end, it seems to be quite similar what you're doing and what he's doing, but not exactly, because you don't need to fit the EBE. You just simulate the beta. So I'm just wondering whether you're not more or less converging to the same kind of thing
maybe we are.
for the approach, and that you have to linearize around the eta at high.
Yes, that's the thing what I wanted to say with the last slide, for example, that it was my last slide. I, for example, I talked with Joakim
Yes.
earlier this workshop that there's still, with my thing, for example, that I still have to look at this empirical base estimate, what Joakim is doing, and I think probably then there will be similar results, but not exactly the same results.
yeah, I mean, it's still approximation to take this expected value over data and say that you will get an expected EBE that performs similar as doing many EBEs and calculate the fin for all of them.
Because then you will, because I think the problem of shrinkage that you,
Yeah, even though it didn't.
perhaps it won't be
be
there.
there.
I don't know. It's just guess. But it's your PhD student, you work.
But yeah, I'm still
Let's see
surprised that
next year.
it performs so well, even though this massive shrinkage actually.
Other questions to Joakim? Other questions maybe to Tobias, since we cut the discussions a little bit short? Well,
Yes, the question is, do you think that all these problems occurs also in GLMMM? Because in GLMMM, we've seen talks where they're all using FO approximation or
Yeah,
MQL. They call that MQL, but it's FO.
yeah. I mean,
So you think they will have the same kind of problem, or it's going to be very different? Okay, I know you've been working
I
on
think you have a shrinkage in GLM and as
How
well.
does that is?
we may ask Dave Woods if Dave has any comments about situation with GLM.
Because I think you have the same problems more or less.
It's very, very similar, right? And I think what we found is the same kind of things that you found originally, but the slightly counterintuitive result that the simpler approximation seems to work better than the more complicated approximation. So the question is whether there's a more complicated approximation
Yes.
that will work better than the
Yes.
simpler one.
Okay.
Well, if there are no more questions, then let's thank both speakers.